What I want to do now is spend a little time explaining a little computer program I wrote a while back that specifically shows the Cottrell equation. And I'd recommend that you maybe play a little bit with the Cottrell equation in this program, which is under the download section of the web page. So if you go to the web page, you can find it there. It's under the download. It's called Cottrell. And I'll bring it up on the computer screen. You see it here. And basically what it does is just plots those equations that we derived in class. And you can change some parameters. You can see the number of electrons, the area, the diffusion coefficient, the concentration. These tend not to be so critical. Two critical parameters are these two down here. One's the t range, which is the time range, and it's set now for 10 seconds. And the other is the x range, which is the distance out in solution that we're going to be looking at. Because we're looking at an area of a region of the electrode solution interface, we want to specify how far out. So we can think, well, let's look at only the first 10 micrometers, or let's look at the first 100 micrometers of that interface. And so we're looking at here the first 100 microns, or 0.01 centimeters. And let's first of all show you what happens under linear diffusion conditions for the area. And so let's show that here. And what you're seeing is a plot on the top here of current versus time, and it's going to go out to 10 seconds. And obviously it's not quite real time, but there's the current that you would observe for these particular conditions, and this is the time, so there's 5 seconds. And what you can see is that t to the minus 1/2 behavior as we predict. Down here in the bottom, you see the concentration of species O as a fraction of the bulk concentration. Whoops. And this should say x, and the thing erased it. But what you see is the gradient, and you see at t equals 0, and then I show kind of in animated form the previous gradients. And you can see that at shorter times, that gradient is much steeper than at longer times. In fact, it's kind of linear at very long times, as you'd expect. Now, that's only because we're only looking at that first 100 microns of solution. So if we drop back and look at the first millimeter of solution, we get a little bit different view, but you can still see that that gradient will be varied. Of course, the time doesn't matter because we're only looking at that concentration thing. All right, and so let's stop that here. And let's change the time to a little bit longer time scale. Let's make it up to 1,000,000 seconds. Let's see what happens. Now here the gradient drops to very low values almost immediately because we're looking at times that are fractions of 1,000,000 seconds. So, but notice the current is going to drop to pretty small values, although on the time scale in which we're plotting it, it really doesn't look any different than it looked before. At all points, we're going to get this t to the minus 1/2 behavior. But if you do look at the diffusion current, you'll see that it's 1.8 nanoamps, 180 nanoamps about there. Let's go back to 10 seconds and 100 micrometers. And you can see the current at the end is going to be closer to 100 microamps or so. So that longer time scale, we do get less current. So for a linear diffusion problem, we basically get the same result that you'd expect from the theory, and that's what we've already derived. And you can see this linearizing as the slope becomes shallower and shallower, the current drops off to reflect that. Now, as I mentioned, if our electrode response is no longer considered to be planar, that can be considered to be either a distortion or a disagreement between actual and theoretical, or we can actually derive the current time behavior for spherical electrodes, and we can pop that in, and if we do that now, we can add a spherical diffusion event. And in this case, what we're going to do is we're going to assign a radius to our electrode. And so in this case, we're going to make our radius of our electrode what it would be to give us the same area as before, about 0.28 centimeters. So let's compare. We had, at the end, a diffusion current of about 54 microamps. When we put in a spherical electrode, the basic effect is that at longer time scales, the diffusional process is not limited by the, well, with the linear process, what happens is that as soon as we remove all material close to the electrode, it has to diffuse into to have new. Whereas in a spherical process, there is actually a more efficient spherical, more efficient diffusional process feeding material into it. And what we'll see actually a little bit later is how that works. Let me change the time range. It doesn't look that much different on this time scale, although if you do look very carefully, it does look slightly different at the longer time scales. Let's make our time a little bit longer. Let's go back to that millisecond time scale range and the 1 millimeter thing. Now let's do that plot. First of all, remember before with linear diffusion, that gradient was nearly flat at this point. It's not now. Also notice the current changes much more slowly at this long time scales, and that's a reflection of the different diffusional process. It's the same basic problem, except that we've gone from a planar electrode to a spherical electrode. And so all we've done is really change the diffusional process, the mass transport to the system. And by going to a spherical electrode, we've made the mass transport more efficient, and we've made it so that instead of going to 0 at long time scales, actually we go to some fixed value at long times. And at 1 million seconds is not a very not a kind of experiment we'd be interested in doing typically, but what we can do is we can observe the spherical electrode response if we go to, say, a 30 micron radius electrode, go back to 10-second experiments, and look at time scales again that are, say, 100 microns next to the surface. And now we see this approach to a nearly constant value with our smaller disk, even at times that are about 10 seconds, 5 seconds or so. So by making the electrode smaller, we've made the time to onset to the spherical diffusion effect much more rapid. At short time scales, we still see this effectively what looks like linear diffusion here. And if we looked at even shorter times, it would still look like linear diffusion until it gets long enough that the spherical diffusion part takes over. Let me just show you quickly. If I switch from spherical to planar, you see what happens. Notice the shape of the concentration gradients in the planar diffusion field. Go back to spherical, and you can see there's a lot more current for the same area of electrode, and the gradients are much less shallow. And we can drop back and forth between the two to see that effect. So there's the very shallow gradients for linear diffusion, the less shallow gradients giving us larger currents for the spherical diffusion. And so, and you can see where with the linear diffusion there is really no, everything scales with time directly, so it doesn't matter what the area is, it's just the scaling factor. Whereas with the spherical diffusion, the area actually has a significant effect on the shape of the current time behavior. So that does suggest that in addition to area in the spherical diffusion situation, you're going to have another variable that will be a radius in the expression. And so again, I would suggest that you maybe play with that a little bit, and you can see where things are going, and you could probably maybe even plot these theory versus time on a spreadsheet and plot them and see the proper shape of the current time relationship. Okay, how are we doing here? We got a little bit more time. All right, let's look at another little part of the experiment. We've said we've looked at the case where we've looked at what we call the Cottrell expression. Let's look at the case when we can allow arbitrary potential steps. And now in the Nernst case, we only allow potential steps out to the point where we had C at the electrode surface was equal to 0. If we allow arbitrary potential steps, that means that C concentration at the electrode surface at all times greater than 0 may not be 0. In fact, it'll be some function of either the Nernst equation or the kinetics of the system. So let's first discuss only the situation when we have reversible reactions. In other words, at all times we're at equilibrium. And that's not always the best assumption, but that makes it simpler to solve. So in other words, the Nernst equation can be used to help us solve the equation. Whereas if we didn't allow reversible reactions, the Nernst equation could not be used because the Nernst equation is only for equilibrium systems. All right, so let's go back to our standard equation. And you can see why we derive that, because we don't have to rederive it. We can always go back to the Laplace space, and then we can put in just a new boundary condition and get a new equation for a different condition. Okay. Okay, what are the other conditions? Well, we're going to maintain the boundary condition that for time is equal to 0. Concentration of O is going to be equal to the bulk. And also we're going to maintain the boundary condition as we've already had in the thing, the concentration of R at all times is equal to 0 at the electrode surface. Well, wait a minute. Yeah, at time equal to 0. All right, so since we have to consider the concentration of R, we now why do we have to consider the concentration of R? Well, we have to consider the concentration of R because since we're doing an arbitrary potential step, there will be two parts of the system. We'll have oxidized and reduced molecules can be present simultaneously at the electrode surface. So we do need, because we're going to use the Nernst equation, we need to know both concentration of O and the concentration of R. So we can substitute in what R will be. Now it will be the same equation as here for O, except that there will be no initial concentration of R. There's no bulk concentration of R present. So that term drops out, but there will be a B term which will have to be solved. And so we've got C sub O bar, and we've also got C sub R bar as something to consider. Now, what makes this simpler for us to solve is we have a flux balance equation that can be used. And the flux balance or the mass balance equation in the Laplace plane is equal to this. Now we can take the derivative of these and substitute, we take the derivative of this and we can substitute these expressions in, and what we'll do is get the following equations. If we take the derivative of these and substitute it into these equations here, we get minus a sub s, or a is a function of s, d to the 0 1/2, s to the 1/2. That's something we've seen before, and we get then on the other half, that's due to the species r, now the Laplace variable s to the 1/2 cancels out under these conditions, and we get b to the s equal to minus a to the s, and we use this symbol, I forget what they call that in Greek, but, and that is just a shorthand way of specifying this ratio dO over dr to the 1/2. Now, often we'll just make that equal to 1, assuming that the diffusion coefficient of O and R are the same, but sometimes we can't make that assumption. So that's nothing that we haven't done before, and we haven't really applied any new boundary conditions to the system at this point. What we can do now, though, is apply our new boundary condition that suggests that we will have an arbitrary potential step, and then it also will be at equilibrium. So the reversible boundary condition requires equilibrium to be maintained at the electrode surface, and we know that under those conditions that means that we can use the Nernst equation. So the Nernst equation can be used as a boundary condition in our system. So E is equal to E0 plus RT over NF, natural log. And the Nernst equation applies in the bulk, but it also applies at the electrode surface. As long as we've got a certain potential at the electrode surface, the ratio of the concentrations at the electrode surface will be given by the Nernst equation at equilibrium. We can rearrange this a little bit to make it easier to deal with. For example, we can write the ratio of CO over CR. We'll use the Greek letter theta to indicate that ratio, and that then becomes equal to E to the NF RT E minus E0 prime. And the Laplace transform of that is the only part that really changes in the Laplace space, and the concentration of O is OS, concentration of R OS is equal to theta, because these terms don't get changed in the Laplace space. All right, just a few more steps. That's quite simple, actually, once we've already derived the Cottrell equation. So all we have to do is take this boundary condition and use it just like we used the other boundary condition as before, which was at all times the concentration of O at the electrode surface is 0. In this case, this is the new boundary condition that we're going to be using. And I'm not going to actually go through that. You can actually do it yourself. I would recommend it to make sure you understand what's going on here. It'll save a little bit of time. Just write down the expression. And notice so far it looks a lot like the Cottrell equation, but we've added in a term which is equal to 1 plus that squiggle squiggly e times theta. And let's define a value I sub d, which we'll define as the Cottrell expression. So this is the value that we can use, for example, as a normalizing value of the current. This would be the value for the Nernst, not the Nernst equation, but the Cottrell condition, where the current, where we make that one condition where we step all the way to the plateau. If that's the case, then I is always going to be equal to ID over 1 plus squiggly e times theta. Okay? So all we need to know is the Cottrell equation and that squiggly e theta to derive the relationship for any particular potential that we step to, as long as we make the additional assumption that we've got still reversible case. In other words, we've got rapid kinetics. So if we plot current versus time, we've got a kind of a complicated plot here, but let's see if we can get through it. We can draw, we'll get a curve that would be, for example, for squiggly e theta equal to 0. And that basically means that E0 prime, or E is very negative. In other words, we're well past the E0 point, and we're at a point where we'd have basically the Cottrell would hold. So this is essentially the Cottrell curve. It is exactly the Cottrell curve. And then we would get curves that would be something like this, that essentially would just be scaled for different values of E theta. And so on. And you can see how those curves would take place. And so what are we doing? These E thetas are different potentials that would be on the curve somewhere. All right, somewhere along that curve. So if we draw that, I guess we have it on in the notes, and you can see E theta approximately 0 here on the plateau. Of course, it will never be exactly 0. To be 0, it'd have to be an infinite potential, but it would basically be 0 at that point. But then we'd have values of 2 and 1 somewhere along the curves. So let's just say, for example, that would be E theta is equal to 1 here, E theta equal to 2 under those conditions. One last thing for this idea. We can actually think about taking and monitoring the current as a function of some time. Rather than measuring the whole curve, we can actually think, well, let's measure the current at, let's say, a time that's we'll call tau, or tau prime, or tau double prime, whatever we want to talk about. What we got here is a set of current time points. And if we plot a current potential, well, actually it'd be more, this would be a better better value for that. What we get is a set of what they call a sampled current voltammogram. Where each of these circles would be essentially the sampled for, say, values at tau, tau prime, and tau double prime. So essentially, we're going down and we'd sample for a bunch of different E thetas along this tau line. And if we do that, and we plot the current that we measured at each of these points along one particular value of tau, we get a curve that looks just like this. That's what they call a sampled current voltammogram. And what you see then is, for a reversible case, the E1/2 value is equal to E0 prime. So this is one way to generate a value, a current potential curve. And then the mass transfer coefficient for these would be some function of time, as you'd expect. We can derive that later. Okay. And, now, for any given time, for a fixed tau, the current as a function of tau is equal to the I sub d value at tau 1 minus squiggly E theta. And that's just what we've written before over here. And so given what we know already about the Nernst equation, the way we've defined it, we know that this is true, and then also theta is equal to I d tau minus I tau over squiggly E I tau. So E0 prime equal to RT over NF okay. Remember that this is the squiggly E term here, d sub R over d sub O, plus RT NF natural log E1/2 is equal to E0 prime minus RT over NF. Natural log of this term here, or again using the squiggly E term like so. So these equations is the same exact equations as we derived in chapter 1, where we actually used a semi-empirical parameter. We used that mass transfer coefficient. Here we've actually derived using real mathematics the equation that we predict and that we derived using the semi-empirical methods in chapter 1. So we have a good correspondence between a sort of a simple hand-waving type derivation and a more rigorous derivation here. And so that's what we're looking for. So we need to see a nice correspondence. That current potential curve then is dependent on the time that we sample, but that's the only thing it's dependent on. Okay. Well, I'll stop here. We've probably gone far enough.